Hello everyone. Today I'm gonna continue my lecture on mathematical Olympiad problems around the world. In today's lecture, I'm gonna go over two functional equation problems. The first one was in the Uzbekistan National Olympiad in 2014. The second one was in the IMO Training Camp in 2012. In the last section, I'm gonna discuss the connection between these two elementary problems with modern mathematical physics. To be more precise, I'm gonna discuss about wave turbulence theories. Now, let us start with the first problem. This is a functional equation. We need to find a function f from R to R that satisfy this relation. You have f of x cubed plus f y cubed will be x plus y times f x squared plus f y squared minus f the product of x and y. This should be satisfied for x and y in the real line. Now let us discuss the solution. First, I write down the equation. This is the equation that I have. In this equation, if I put x and y to be 0, this will become 0, this will become 0. But the important thing is this factor will be 0, which means that the whole thing on the right hand side will be 0, and finally you get f0 is equal to 0. Now I'm gonna plug x to be minus y. Why should I plug x to be minus y? Because that makes x plus y 0. This means that I get f of x cubed plus f of x minus f of minus x cubed will be 0. In other words, x is an odd function. Now I'm gonna replace y to be 0. When y is 0, I replace 0 here, which is 0. I replace 0 here, which is 0. I replace 0 here, that makes everything 0. I replace 0 here, it is also 0. So the leftover is this one and this one. In other words, I have fx cubed is x fx squared. Now I replace all of the information that I have. Then I'm gonna get f of x cubed plus y cubed will be xf squared plus y f squared, fy squared. Now, when you simplify this equation, the whole equation, you're gonna get this relation, which is very nice. You replace y to be 1 in this equation. So here you're gonna have 1 here. This become fx squared. This will become x f1. Finally, you get this equation. Now you're gonna plug x to be minus 1. You do the same thing. You replace minus 1 here, minus 1 here, and minus 1 here. But you remember that f of 1 and f of minus 1, they are the minus of each other. In conclusion, you get this relation, which means that fx is x times f1, so this gives you the solution f is c times x, where c is a constant. The second problem that I want to discuss is this problem. Suppose that f is a function from the real line to the real line. Suppose that f of x plus y plus xy is fx plus fy plus fxy. You're gonna have to prove that f of x plus y is fx plus fy. Now let us discuss the solution. First, I write down the equation. Again, I'm gonna use the same method. I plug x to be 0, y to be 0. Then on the left hand side you have f0. On the right hand side you have 3 times of f0, which means that f0 is 0. Now I'm gonna replace x to be minus 1, y to be minus 1. Here I have minus 1, here I have minus x. Here I have x, here I have minus 1. So y is minus 1, but here I also have minus 1, so the two yellow terms will cancel. This one will become f of minus x. This is why I have f of minus x is minus fx. Now I'm gonna replace y to be 1. Then here I have 1. The whole thing on the left hand side will become 2x plus 1. The whole thing on the right hand side will become 2fx plus 1. Now, let us consider this complicated expression. This is 2 times of xy plus x plus y plus 1. I'm gonna use this formula. I will have 2 times of xy plus x plus y plus 1. Now let us look more carefully into f of xy plus x plus y. For this term, you can use this equation. When you replace this equation into this term, you're gonna get this one. On the other hand, let us look carefully into this term. The one in the bracket can be written like this. Now, you apply this formula again, you will get this formula. Now I'm gonna apply this formula, this yellow formula, to f of x, 2x plus 1. I'm gonna have 2fx plus 1. This is why at the end of the day I'm gonna have this formula for f of 2xy plus x plus y plus 1. But from the previous relation we have this term. Now we identify the both term. We're gonna get f of 2x plus y, 2xy plus y is fy plus 2fxy. Now I'm gonna plug x to be minus 1/2. You have f of y will be 2fy over 2. You combine this with the previous equation, you have f of x 2xy plus y is fy plus f of 2xy. This is because you combine this equation with this equation. Finally, this is the equation that we got. Now, if v is 0, then f of u plus v is fu plus fe, right? If v is different from 0, you're gonna put x to be u over 2v, and y is v, and you apply this formula, and you also have this equation. Finally, fx plus y is fx plus fy for xy. We have a remark. If f is continuous, the solution of this equation is always the linear function cx, and c is some constant in R. Now, in the two cases, we know that we observe that the solution is always cx. What is so special about this? Let us discuss the so-called wave turbulence theories. This theory is used to describe non-equilibrium statistical systems of many randomly interacting waves. This theory has a lot of application. The first application is in optics. In this system, you have interacting wave and solitons. Another application is wave turbulence on ocean surface, and this has application in wave weather forecasts. Another one is solar wind. So in solar wind, you have even wave, and then you need a wave turbulence theories to describe this wave turbulence system. In fusion plasma, you also need wave turbulence theory. And other things are wave like capillary water wave, waves in laboratory films. In conclusion, this wave turbulence theory has a lot of application in our real life. Now, what is the connection with the previous two mathematical Olympiad problems? Let us consider one wave K1. This wave is broken into two waves K2 and K3. But you also have the case where the two waves K2 and K3 combine into the wave K1. If I denote K to be the wave number of the wave, then I have to have the conservation of momentum. So omega K, K1 have to be equal to K2 plus K3. This is the conservation of momentum. But in this, we also have to have the conservation of energy. If I denote omega to be the dispersion relation, which is a function, omega is a function of the wave number, then I also have the conservation of energy. So in general, I'm going to have the system of two equations. K1 is K2 plus K3, and omega K1 is omega K2 plus omega K3. Omega is then a function of the wave number K. Now, if you want to study the system, the first thing that you have to find is the equilibrium of the system. The equilibrium of the system is a function E. This function satisfies this relation. For the vector K1, K2, K3 satisfy the conservation of momentum and the conservation of energy. Now, if you define HK to be 1 over EK, this is a mistake, then I'm gonna have H of K2 plus H of K3 is H of K1. Now, we need to solve the equation H of K2 plus H of K3 is H of K1 is equal to 0 for a K1, K2, K3 that satisfy this equation. Of course, when D is 1 and omega K is K, we come back to this equation. Omega K2 plus omega K3 minus omega K1 is 0 when K1 is K2 plus K3. And the solution, as we know, is CK. Then the equilibrium will be the reverse of H, which is 1 over CK. Of course, in the general case, omega K is not K and D is greater than 1. Then the equilibrium has also a very similar form, C over omega K. However, the proof is much more complicated. So the conclusion is that in modern wave turbulence theory, in order to find the equilibrium, we also need to solve functional equations that are similar to the two equations that we consider in the previous two sections. Now, I just want to mention that here I make a typo. HK should be 1 over EK. This formula is not true. This formula is true only in the quantum case. But here we are considering classical wave system. So HK is the reverse of E only. Thank you so much for your attention.